In this video, we're going to learn how to construct confidence intervals for means and deal with inference about means. There are two distributions used when we're making a confidence interval or interval estimate for a mean. And which distribution we use has to do with whether we know the population standard deviation or we don't. If we know what the population standard deviation is, we're back in week 3. We're working with the standard normal distribution for a sampling distribution. And we know what the z-curve looks like. Has a mean of 0, has a standard deviation of 1. If I want to calculate probability, I'm using normal CDF. If I want to find a z-score given a probability, inverse norm. So that's familiar footing. The problem comes when we don't know the population standard deviation. In that case, we want to be extra cautious because we don't know how spread out the data is about the mean. In that case, we use something called the student t-distribution. The student t-distribution is very similar to the standard normal in that it is symmetric and bell-shaped, and it's centered about 0. But its standard deviation is bigger than the standard normal curve, and that standard deviation, or the spread of the t-distribution, depends on something called the degrees of freedom. And for inference for a mean, a single sample question, that degrees of freedom is sample size minus 1. We have similar functions for the student t, just like we did for the normal distribution or z-distribution. There's a t-CDF function on most calculators if we want probability, and there's an inverse t if we want t-scores instead of z-scores. For confidence intervals, we're strictly going to be down here with the inverse norm and inverse t, because we're going to be looking for critical values. Critical z values or critical t values. So let's go through the 3 steps that may look a little bit different. We know we're doing state, plan, do, conclude. We know state is just breaking down everything that was given in the problem and slapping it down on the page. For plan, you're going to state the method that you're using. If you know sigma, then it's a z-interval for a mean. If you don't know sigma, it's a t-interval for a mean. The reason that's important is you're going to be finding a different critical value. Your interval will be narrower if you're working with z. It will be wider if you're working with t. For a z-interval, to find your critical value, you're going to figure out the area in the left tail. Because what we're doing is we're building a normal distribution. We're putting our confidence level here in the middle, and then our z-scores are these boundary values, which are very messy. To do that, I need to know how much area is in that tail. So we're going to take our confidence level, that's this, we're going to subtract it from 1, because that's the area under the whole curve, and we're going to divide it by 2, because it gets split between the left and right tail. Once you've done that, you go to inverse norm, second vars, and then you plug in the area you just found, 0, 1 left. When you do that, it's going to give you a negative z-score. Your critical value is the positive version of that absolute value. You should draw that picture that I just sketched, draw the normal distribution, put your confidence level in the middle, mark negative z and positive z. to demonstrate that you understand where those tails are coming from. If you don't know sigma and you're working with the t-distribution, the process is very similar, but you need to know your degrees of freedom first. So after you've written down that you're doing a t-interval for mu, you're going to write down df equals and then sample size minus 1. Plug those numbers in. To find the critical value, once you've done that, is very similar. You'll notice area in the left tail, 1 minus the confidence level divided by 2. And instead of inverse norm, we're using inverse t, which only asks for 2 pieces of information. What is the area in the tail? What is the degrees of freedom? Just like inverse norm, you want the absolute value of that answer because it's going to spit out a negative. And you should draw a t-curve, which looks exactly like a normal curve, right? Nice, pretty bell-shaped. Confidence level in the middle, negative t, positive t, CL sitting here. And we'll do a couple examples so you can see what that looks like. Now that the setup's done, we're going to go to the do, which is really quick. If you know the population standard deviation, copy that formula down, plug in the values, use your calculator, stats test z-interval. If you don't know the population standard deviation, this formula, write down the equation, plug in your values, use your calculator, t-interval. So pretty straightforward. Once you've figured out whether you know the population or don't know, it's following directions, right? Z-interval, t-interval, formula, plug in values, plug in calculator. Once the do step is done, we're going to go to conclude, which is the same regardless. We have a sentence frame that we're going to fill out. We are blank % confident that the interval from blank to blank captures the true mean blah. You're going to put numbers here, so this is your confidence level. These are the boundaries that you found for your confidence interval, the 2 answers that came out of your do step. And context from the problem should include what you were finding the mean of, true mean height of all U.S. adult men, and the population of interest. We're going to do 4 examples, or 5, I think I may put 5 in here, so you can see how this works in practice, because I think that's probably the hardest part of this process. So for our first example, it says, suppose average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. A random sample of 28 pizza delivery restaurants is taken and has a sample mean delivery time of 36 minutes. Find a 90% confidence interval estimate for the population mean delivery time. So we're going to go ahead and do our state plan do conclude. So step 1, I'm doing my state. I'm identifying everything I was given in the problem. So I'm going to go ahead and circle that down here in blue. So I'm told pizza delivery times are normally distributed. So the thing I'm looking at, pizza delivery times. I know my population standard deviation is 6. Ooh, sorry about that. I know I have a sample of 28 pizza delivery restaurants and that the sample mean is 36 minutes. So first let's write that down. So we know X equals delivery time. And we know X is normally distributed. We know we have a population standard deviation of 6 minutes. We know we have a sample size of 28 pizza times and a sample mean of 36 minutes. The other thing I should do is identify what I'm being asked to do, and that's that second sentence. It says find a 90% interval estimate for the population mean delivery time. And it's this 90% confidence interval that's big for me. I know that I'm asked to find 90% confidence interval for the population mean mu. Now that I've summarized, my next step is the plan. So I'm going to state what I'm doing. And I know for means, the first thing I do is ask myself, do I know the population standard deviation? And the answer is yes. They gave it right here. 6 minutes. If I know the population standard deviation, this is a z interval for the mean. Whoops, that's not how you spell interval, Mr. Jolliffe. And I know if it's a z interval, I need a z critical value. So that's the next thing I'm going to do here. I'm going to draw my normal distribution. I'm going to mark my critical value level in the middle, 90%. That's my minus z star, that's my plus z star. And if 90% is in the middle, that leaves 10% for the tails. And I have to split that 10% in half. So 5% goes here, and 5% goes here. To find my z star, I'm going to use inverse norm. And I need area in the left in decimal form, so 0.05, 0 and 1 for the standard normal. And then if your calculator is the newfangled version, left. This is a z. So let's go ahead and do that really quick. So second vars, we want inverse norm. Our area is 0.05, mean of 0, standard deviation of 1. And I get negative 1.6448. This is commonly rounded to 1.645. So I'm going to write down z star equals 1.645. I'm halfway done. Next is the do. And the do is grab the formula. So for a z interval for a mean, x bar plus or minus z star times standard deviation over the square root of the sample size. My next step is I'm going to plug those values in. I know my sample mean is 36 minutes. I know that my z star is 1.645. And then for my fraction here, I know that my population standard deviation is 6 minutes, and I have a sample size of 28. At this stage, we grab our calculator. You can evaluate that manually, or we can do our z interval. So on our graphing calculator, to pull up those statistics formulas, stat, tests, and we want z interval, which is option 7. And in this case, I have statistics. I wasn't given a raw list of data. So I'm going to go over to stat, and it's going to ask me for that information I wrote down. So 6 minutes, a mean of 36 minutes, a sample size of 28, and a confidence level of, confidence level of 90% if I could not delete things. And then we run that, and it gives us two numbers, 34.13 something and 37.86 something. Ooh, hang on a minute. Sorry about that. Alarm. Sorry. When I write this down, I'm going to give it to one more decimal than the values I was given. Everything in the problem was a whole number. I'm going to round this to one decimal place. So when I write my interval, I'm going to write lower bound first, 34.1 minutes. Oops. And then comma, and then my upper boundary is 37.86, which is going to round up to 37.9. So our interval estimate for our mean is 34.1 minutes to 37.9 minutes. And I'm going to formalize that in step 4 with my conclusion. And my sentence frame is that we are 90% confident, because we used a 90% confidence interval, that the interval from, and then I'm going to state my interval, 34.1 minutes to 37.9 minutes, captures the true, whoops, I know how to spell. Maybe I don't. True, mean, and then context from the problem. And it says, I'm asked for the population mean pizza delivery time. So captures the true, mean pizza delivery time. So that right there is a complete solution for a confidence interval question. Step 1, identify everything that's given. Step 2, state what you're doing. Find any additional values that weren't given that you need. Step 3, write down equation, plug in values, use your calculator. Step 4, interpret your answer with a sentence. I'm going to do the next couple a little bit quicker, just because we've seen it long form and I want to do these examples a little bit faster. So moving on to example 2, I'm going to write as I read. So it says, you do a study of hypnotherapy to determine how effective it is in increasing the number of hours sleep subjects get each night. You measure hours of sleep, so we know our variable x is hours of sleep. We measure hours of sleep for 12 subjects, n equals 12, with the following results, and we don't have anything else. We have raw data. It says construct a 95% confidence interval for the mean number of hours slept for the population from which you took the data. So in this case, I'm asked for a 95% confidence interval for mu. And I'm not given any other information. I'm given raw data. I know from experience, if I go back up, when I do this, I need a standard deviation. I need a sample mean. So I'm going to use my calculator to find an x bar. Nowhere in that question, if we read through it, was I given a population standard deviation. meaning I don't know my population standard deviation, so I'm going to need to use my calculator to find a sample standard deviation. So we can do that using our calculator really quick by putting that list in a data and running 1var stats. That's something that we learned how to do in week 1. So stat enter, maybe. We're going to clear out that list and type our values. Oops, I mistyped that. That should be 9.2, 7.5, 10.5. And then for 1var stats, we go over stat, calc, enter, enter. And I can see that my mean is 8 point, and I'm going to round it to 2 places because my data was out to 1 place. So 8.98. And my standard deviation SX is 1.92. Ooh, 2.9. Order is important. The nice thing is now that I have that data in my calculator, that's going to help us when we get down to step 3. Step 2, we state what we're doing. Because we don't have sigma, we're using a t interval. And we need to find our critical value at this stage. And we know our critical value depends on degrees of freedom, which is sample size minus 1. So we're working with degrees of freedom 11. We're going to draw our picture really quick. I'm sorry, my hand is so shaky. We put our 95% in the middle. We have our negative critical value and our positive critical value. I'm going to zoom in a little bit. I need to know the area in the tail. If 95% is in the middle, that leaves 5% for the edges. And if I cut that in half, that's 2.5% in each tail. So we're going to call inverse t, which asks for area in the tail in decimal form, and our degrees of freedom. So let's pull up our calculator again. And we go second vars inverse t is option 4, 0.02511. And we get negative 0.2009, which is 201. So 2.201. T values are typically rounded out to 3 decimal places. Z values typically 2, except the one we saw in the last example. If you forget, an extra decimal place is always better than being short one. But typically 2 to 3 decimal places for critical values. For step 3, we do the math. We grab our formula. Sample mean plus or minus critical value times standard error, which is standard deviation divided by square root of sample size. And you'll notice, because I didn't have sigma, my standard deviation is now S. Same process, we plug the values in. 8.98 plus or minus 2.201 times, and then for the fractions, we know our standard deviation is 1.29, and our sample size was 12. Here we go back to the calculator, and we know we're going stat We're going tests, and now we want t interval, which is option 8. And this time we do actually have data. We took this set of data here and put it in list 1 at the beginning, so I can leave this on data. I'm going to tell it where my data is. It's in list 1. We shouldn't have a frequency list. We can leave that as is. And our confidence level for this problem was 95%, so 0.95. And when we do that, we get 8.16 to 9.80. Last step, we want to interpret. So we are 95% confident that the interval from 8.16, and in this case, if I scroll back up, X was measuring hours of sleep. So this is 8.16 hours to 9.80 hours. Captures the true mean, and then I'm going to give context from the problem, hours slept for the population. And in this case, this was hypnotherapy, number of hours sleep subjects get. I should have, oops, that's not what I meant to do. Hours slept for. And again, you'll see the state plan do steps laid out nice and pretty. Stated values given, identified the method, found those relevant values, formula and calculator, sentence to conclude. I'd like to do one more that's a little bit different. If you need more examples, feel free to drop by office hours or let me know and I can record an additional video. But this example says, a sociologist wishes to estimate the average number of automobile thefts in a large city per day within 2 automobiles. He wishes to be 99% confident, and from a previous study, the standard deviation was found to be 4.2. How many days should he select to survey? So we're going to start this the same way. I'm going to list what I was given and what I'm asked for. So I'm interested in estimating average number of automobile thefts in a large city per day. So X equals number of auto thefts in a day. We're told he wishes to be 99% confident, so we're working with a confidence level of 99% or 0.99. Says from a previous study, the standard deviation was found to be 4.2. We're assuming, since we weren't told it was a sample value, that that is a population value. And it says, how many days should he select to survey? Notice they didn't say construct a confidence interval. They asked how many days should we survey. They're asking what our sample size should be. there's one more piece of information that we didn't list here. And it says way back in that first sentence, sociologist wishes to estimate the average number of automobile thefts in a large city per day within 2 automobiles. When we give a margin like that, where it says within 2 automobiles, within 5%, within 5 centimeters, what they are giving you with those keywords is the margin of error. They are telling us that our margin of error, our EBM, is equal to 2. This is going to feel a little weird because it's related to a confidence interval, but we're not actually going to build the confidence interval. We're going to find the sample size using the margin of error piece of that confidence interval. So this is still a confidence interval question, but we're not actually going to finish the confidence interval. We're going to focus specifically on that margin of error piece. Because we are looking at confidence interval for a mean, even if we're not going to build it, I am still going to write Z interval for a mean, as that is the formula I'm pulling from, and I know it's Z because I have sigma, and I am going to find that critical value just like I would for a confidence interval. I build my Z distribution, I mark the middle 99% minus Z star plus Z star. I know if 99 is in the middle, that's 1 for the tails, which means that's 0.5%, 0.5% for each tail. So I'm going to run inverse norm, and then 0.5 is 0.005 in decimal form, mean of 0, standard deviation of 1, looking at a left tail, and that'll give us our Z star. So second vars, inverse norm, 0.005, 0, 1, and we get negative 0.575, so negative 0.58, negative 2.58 rather, so 2.58 for our critical value. And then for step 3, I'm not using the whole interval, I'm just using the margin of error part. We know the margin of error is called the EBM, and we know that it's the critical value, Z star, times the standard error, sigma over square root of n. If we solve this for n, doing some algebra, first I need to get n to the left and EBM to the right, so they change places. I end up with a Z star times sigma over EBM. And then I have to undo that square root on the n, and I do undo square roots by squaring, so this whole thing is going to be squared. My next step, I'm going to go ahead and plug my values in. So sample size is equal to, I know my critical value is 2.58 times, I know my standard deviation is 4.2 and my error bound is 2. And I want to square that. Unlike confidence intervals, there isn't a built-in formula for this on the calculator. There isn't a function call. We're going to have to type this in. So parentheses 2.58 times 4.2 divided by 2, and then I'm going to square that whole thing, and we get 29.35, so 29.4. And I can't sample 29.4 days, or 29.4 people, or 29.4 cogs in a machine. I want my sample size to be a whole number. And generally, to guarantee that we have at least within 2%, if not closer, we want our sample size to be bigger rather than smaller. So this is generally rounded up to the nearest whole number. So when I write my conclusion, I'm going to say he should select, because that's what I was asked here, how many days should he survey? He should select 30 days to survey. Again, steps 1 and 2, identical. If it's a confidence interval for a mean or anything related to confidence interval for a mean, that state and plan steps will look the same. For step 3, if it's a confidence interval, grab the confidence interval formula, use the function on the calculator. If it's a sample size, grab the sample size formula. I have it right here, it's also in your textbook. Plug in values, use your calculator, and then write your summary sentence. All right, that's it for inference for a mean. If you have any questions, feel free to send me an email or catch me in our next office hours. Oops, I didn't mean to do that, sorry. For our next video, we're going to talk about confidence intervals for proportions. I'll see you then.